Hello, everyone, and welcome to the 31st episode of TechLifeSkills with Tanmay. My name is Tanmay Bakshi, and every week I go live with the goal of making advanced technology concepts accessible to everybody. Now, we hear from a diverse range of guests on this show, ranging from leaders with decades of experience to students who are just starting their journeys. And we've covered a lot of different technologies during this journey, and a lot of them are brand new, and some of them are in their infancy, some of them are growing really fast, but they all promise new experiences that really wouldn't have been possible without them. But I feel like the technology we're covering today is in a completely different category altogether, in the sense that it has the potential to redefine the way we compute. And this technology is quantum computing. All right. Now, quantum computing leverages quite literally, exotic laws of physics to help us accelerate certain tasks with the power of this brand new compute, faster than we could ever do this on classical computers. And that's why I'm so excited to learn more about the world of quantum today. Our special guest is Anamita Guha, a global lead of product management at IBM Quantum. She was named one of the top 25 software product executives of 2020, and I'm really excited to hear from her. And so, without any further ado, I'd love to welcome Anamita to the show. Hi, Anamita, how are you?
Wonderful. How are you, Tanmay?
I'm doing very well. Thank you for coming on the show. It's an honor to have you here, and really excited to learn more about quantum. Of course. So now, before we actually get started diving into the world of quantum computing and technology, I'd love to hear a little bit more about you. So would you maybe want to, quickly introduce yourself, tell the viewers a little bit more about how you got to doing what it is that you're doing today?
Absolutely. So, I was born in India. I actually moved around a lot when I was little. My bingo fun fact is my first five birthdays were in five different places. I eventually found my way to the San Francisco Bay Area, and both my parents actually worked in tech. So, from an early age, I just had exposure to computers and technology, and I loved it. And I would play around on computers all the time. I started designing websites at the age of 9, and I was designing them for money. And back then, I didn't have a bank account, so I would get them in Amazon gift cards and then use that to um, buy things for myself, Britney Spears CDs, other things. And then from there, I actually just being online and speaking to people around the world, I got really interested in humans and why humans do what they do and what motives them and how cultures and people are so different. So I actually went on to study cognitive science at the University of California, Berkeley. For those of you who don't know, cognitive science is the study of the human brain and mind from an interdisciplinary perspective. And as I was taking courses, I decided I actually wanted to go to med school. And I started jumping through all the right hoops to get myself there. I was really interested in psychiatry and how the brain functions from a neuroscientific level. And my summer before my senior year, I actually ended up founding my first company, which was a test prep analytic company that stemmed from my MCAT studying. And if I was pitching it to investors now, I'd call it AI for test prep. AI wasn't really a buzzword then. I worked on it for about a year and then sold it. And then at that point, I was like, I don't know if I want to go to med school anymore. So I did a search for cognitive science online and I got a job as a product manager. So from there, I worked at several startups in the Bay Area in San Francisco. I worked in advertising, I worked in mobile games, I worked in the gig economy, I worked in big data, mobile. Like anytime there's a big word, buzzword, I was there. I was always at the bleeding edge. And I somehow found myself at IBM, which I now refer to as the world's biggest startup. And when I joined, I was working on out in Watson West, and my goal was to get more developers to build with Watson. So I was running the AI incubation hub effectively. And from there, about 2 years ago, I got a call from one of my mentor sponsors, actually, who was working on the quantum side. And they were just getting ready to pull quantum out of research into more productionized commercial uses. And so they're like, hey, come work with us. So I got on a plane, moved to New York, and now I have been a part of the quantum journey for about 2 years, and it's been really, really awesome. So on the quantum team, I run the product and growth of our community. So how do we get users around the world to be interested in quantum? And those of you that are interested in quantum, how can we make it more useful to you? And sometimes it's cases of I don't even know that you want to be interested in it, but I look at data to figure out, yes, maybe you will be. So we do this in a lot of different ways. We do events, we do some growth hacking, we put out a lot of learning material. We meet with individuals one on one, we partner with universities and students and organizations. And we really just get to know the community, and we're all evolving together. And I'm really excited to grow new and diverse markets for quantum computing.
Wow, I mean, it's so fun to hear that so much of this stemmed out of what you're so passionate about, right? To think that you've been sort of growing from all these different roles within all these different companies, and now you're at IBM, what you call like the world's largest startup. I think that's pretty incredible. And when it comes to quantum computing, what you mentioned about it being pretty recently actually ready to sort of start moving out of research and start moving into sort of more productionized use cases. I feel like that's a really interesting time for technology, especially something like quantum, because while of course there are there's sort of great milestones of quantum technology that we've reached that we can already start to leverage today, there's still a lot of research to be done, and it's interesting for me to see how exactly that research that's being done quite literally as we speak sort of translates over to real world use cases. And I'm already seeing, actually, we've got some questions from the live stream as we speak on like why it's important for people to care about quantum computing. So we will be getting to those in a moment, and of course please feel free to send in any more questions via the live stream chat. We will be covering those momentarily. But Anamita, I do want to start off by asking you though, with this experience that you've had with the world of quantum computing, what would you say it is that quantum computing allows you to do in the first place? Now, I don't want you to necessarily cover the details of how it works, but could you maybe give me an idea of what kinds of use cases it does enable, right? You mentioned there are slightly productionized use cases out there. What kinds of things is it enabling us to do today?
Yeah, so I'll start off with saying we're very, very far away from quantum computers being truly useful.
Yeah.
We're still experimenting and learning, but what I will share is what quantum computing has the potential to do.
Mm-hmm.
And to start, quantum computing is a fundamentally new type of computing. It's a brand it's new from what we know, and because it's new, we're able to solve old problems and some new problems, but in doing both in new ways. So when you approach these use cases, quantum computing has the potential to really threefold. One is to things that weren't possible in a classical computer that we weren't able to realize, we can now do now. An example of that is chemical simulation. So right now in a classical computer, you could probably simulate a few hydrogen atoms, but you can't really simulate a caffeine molecule, and most of us drink coffee every day. So just realizing things that we can't do now with classical computers that we can now potentially do with quantum. The second one is more precision. So this is effectively very important when it comes to things like optimization and scenario simulation. So if I'm mapping how to get from point A to point B through a maze, a quantum computer could ideally get you through that better.
Mm-hmm.
And then the fourth one is in some case, or sorry, the third one is quantum computing in some cases will actually help you solve problems faster. So I like to think of this in maybe like AI and other places where you have more dimensions and you can find patterns more efficiently, and it helps you kind of understand your next step.
Mm-hmm.
So threefold. One is solving problems that we can't do right now, solving problems with more provision, and then potentially solving problems faster than before.
Right. Okay, that's really interesting because there are some limitations that we have within the world of computing, and I feel like the one that I always kind of point to is, I mean, as you mentioned, like with AI, right? We see today that actually, quite literally, right now, not right now. Right now, I was working just before this episode to I was editing a video that I'm going to be uploading to my YouTube channel later today, and it's on the BERT network, of course, which is really redefined natural language processing. And I was like, there's been so much stuff that people have done with BERT. When was BERT released? And I would have thought, based off of the amount of progress that we've made, that it was at least like 2-3 years ago. But I searched it up because it felt so much more recent, and it's just barely been a year. And in just that 1 year, we've gone from BERT to hundreds of models based off of it and derived from it, and all this advancement and multilingual models and things like IBM Project Debater being powered by that
Mhm.
technology, right? And I feel like a lot of this is possible thanks to the hardware advances, enabling us to have faster AI training algorithms that use more data and give us more precise results, right? So I feel like there's a good tie-in with what you mentioned about quantum computing, just like how we've had to have this sort of specialized hardware, things like IBM Research's analog chips for AI, NVIDIA's GPUs, Google's TPUs, these sorts of things. Similarly, there are certain tasks that can really benefit from not being limited to sort of classical mechanics and being able to represent their states and represent their techniques within this sort of quantum mechanical world that could really benefit. So I feel like that's really interesting.
Absolutely. Something I tell people a lot is quantum computers are not going to replace classical computers. Use cases that you just described, classical computers could be getting the job done in the way that we want it.
Mm-hmm.
But maybe there's instances where a quantum computer could do it
Mm-hmm.
better, more precisely, more efficiently. But I think the future will be where both computers exist together. Like you're never going to use a classical computer or a quantum computer to like something on Facebook. You would want to use it to maybe simulate a model that you wouldn't be able to do before.
Yeah, I
And
feel.
it's evolving so quickly. Like your bird example also, right? We don't really know where we'll be in 10 years. And at that point, maybe there'll be many instances where quantum computing will be more effective.
Absolutely, right. I feel like right now it's almost even hard for us to say, what we can do with it because the technology is so new that yes, there are lots of different use cases, but we don't know where we're going to be in 10 years, and who knows, with more powerful quantum computers, we may invent brand new algorithms that we never thought were possible, right? So you're right.
I don't know. I wouldn't say quantum computing is new. People have been researching quantum computing for decades.
Yes.
In the 80s, 40 years ago, we're about to celebrate the 40-year anniversary of the first like quantum science, quantum computing gathering that had happened. It happened at MIT. So we have been researching this for so long. It's just we're only those breakthroughs in the hardware, in the hardware that's allowing us to do this so much faster. But quantum science is not a new field. People have been studying quantum science for so long.
Thank you for bringing that up, actually, because that's a very interesting point to me. I feel like there are all these different technologies that we use today. We call them new, and you caught me there. I'm calling quantum computing new. Even though technically you're right, the research has been going on for literally decades, and I feel like that's actually a parallel that we can draw to a lot of different technologies, right? AI, for example, the basic calculus and the perceptron, right? Those have been around for centuries and decades, respectively. And then there's blockchain, and the basics for blockchain have existed again for quite literally decades, but it's just now, thanks to advances in hardware, advances in data, advances in the internet, and these sorts of things, that we are able to finally start actually using these technologies that we've been researching for so long. And so
Yeah.
go
When I
ahead.
went to school for cognitive science,
Hmm.
at that time, this program was so small. And I took a lot of classes in AI and we learned about the history of AI. And the first paper published for understanding neural processing and first time cognitive science or AI was used. And that was decades ago, right? It was in the 1960s, 1940s. People have been researching it on computers and trying to get computers to simulate the human brain.
Hmm.
But now the program was very small, but now it's the third highest growing major in the world. And it's a thing because everyone's so interested in artificial intelligence and quantum computing and these words, but they've been around and it's doing the research of like when did it come out and like how did it evolve is actually a very good exercise, I think, for everyone to do.
Absolutely. I mean, I feel like it's definitely really interesting to look at that history because we take a look today at like I'm sort of going to draw a little parallel to like artificial intelligence here. There are all these different misconceptions about AI and how it's meant to like replace humans and all these things, but I feel like if we take a look into the history of how this technology's evolved and what it's really about, we can really start to understand what it's doing today, right? And how that evolution sort of naturally led to this sort of state where technology is meant to augment humans. And I feel like again, it's not an exact parallel to quantum, but it makes sense, right? Looking into this history, we can see, just how far we've come and just how quickly we continue to innovate. Yeah,
Yeah.
I gotta say, I used the IBM Q experience actually really quickly a couple months ago, and there's this one circuit that I've been really interested in for a long time, the delayed choice quantum eraser, which I translated over from an optical circuit to one on IBM Q, and I ran that a couple months ago, and I actually did a keynote in Oslo where I was demonstrating this, and it was good, but there was enough error to make it not particularly impressive to an audience that wasn't aware of just how groundbreaking this technology
Yeah.
was, right? As a developer, I was like, wow. But then everyone was like, but it's so noisy. And now, you go to the IBM Q experience and suddenly you've got machines with a quantum volume of 32 that you can spin this up on, and suddenly, it's just like the simulations. So I feel like we've really come a long way in a short amount of time.
Oh yeah. I want to touch on the one note you made about just people being afraid of AI taking their jobs.
Mhm.
It's actually one of the reasons why I took this job in quantum computing, because the way we talk about tech now will influence how we use it in the future.
Mhm.
And when I was working in AI, and I still work in AI, but as people talk about AI, it's created this fear, and people don't understand it. So what you're doing with the show is awesome, because it's helping people like understand these topics in a more simple and productive way. And we have an opportunity with quantum computing right now because it's a new technology, quote unquote new, where people are talking about quantum computing for the first time. And if you can help people understand that, like, we are in a phase of where we're getting ready to be quantum, um, for a quantum future, here's how you can be ready and how you can be prepared. And you shouldn't be afraid, but if you're
Mhm.
interested, you'll get started. So and it'll influence so many things. It'll influence laws. It'll influence government sanctions of how computers are distributed and effectively accessed. So you using the quantum computer, like I did quantum experience, is really, really big because from so much of history, in order to access a quantum computer, you needed a physical lab. And by putting the quantum computer on the cloud, anyone can access it. So everyone watching the show right now, you can go and access a quantum computer and run an experiment on it. That's awesome.
And I gotta say, I really appreciate that work that IBM's doing because, I mean, if you think about it, even AI, I would say, right, even machine learning technology, it has been really, it's sort of what's enabled AI to become just so pervasive in our lives is the fact that pretty much anybody can do machine learning research by just going to IBM Cloud and renting out a virtual machine for however many hours they need, right? Or going to the Watson tiles on a cloud catalog and just spinning up a visual recognition instance and building an app, right? That's why AI is so pervasive today. Without the cloud, this technology wouldn't be as impactful on our lives as it is. And I feel like by having technologies like the IBM Q experience, enabling literally anyone to just go there and start experimenting with quantum assembly and building their own circuits, that is driving adoption of a technology that in the future is going to have all kinds of brand new use cases that we can't even imagine yet. So that's pretty incredible. Now there is a question from Akash that I did want to ask you before we continue because I feel like it sort of ties into what we're talking about right now, and he's asking, why should I care about or even take interest in quantum computing? Now, by the way, if you could just speak a little bit louder so we can hear you a little better, that would be great. But yes, why should I care about quantum computing?
Yeah. Well, I feel like there's a quantum scientist in all of us. So if you could be an events person and you're coordinating events or planning things or getting people together. That's what you're an expert in. Or you could be a social media expert and you're very interested in engaging people on social media. All these fields are going to be needed in quantum computing. So when we take the idea of quantum computing being a brand new field that the industry is going to be investing in over time, it's going to open so many jobs. So most simple way of why you should care is there's going to be jobs in it. So if you want a job in it, that's one. The other is quantum computing will be likely around you and influence the world you live in. So you don't know what you don't know, but the more you know, the better you'll feel and the more impact you can add to society and creating and producing more advancements in research and science and really better the world. So I feel like getting involved in something right now as the train's just about to get off is a really unique opportunity. We don't get that often. So and everyone's coming from a place of new. Quantum computing is inherently inequitable. The computer scientists are like, I don't know physics, The physicists are like, I don't know computer science. So take what you're an expert in, what you're interested in, and see how that can relate to quantum computing. Because I guarantee you there's a seat on that train that's about to take off that merges both of your interests and your expertise in the field of quantum computing.
Wow, I gotta say, quantum computing is at that really unique stage where I feel like it's all, I guess maybe not literally, but it's almost like a once in a lifetime opportunity to get on that train, for a technology like this at such an early stage, right? And again, I'm saying early as if this is like a new technology. Again, the basics have been there, but new as in the sense of we're just starting to be able to realize and actually implement the benefits of this technology in our applications. I believe quantum. Yes, go ahead.
One thing I'll give you is we don't know when like the train's going to take off because a
Yeah.
lot of it is dependent on the hardware. So
Mm-hmm.
it could happen in the next year. It could happen in the next 10 years. So
Mm-hmm.
that's one risk to be aware of we don't know how quantum computing is going to evolve or where it will be. But I think the more people that work together, maybe we'll get there faster. If
Absolutely.
we also don't know if we want to do that.
Well, I mean, humans are cooperative creatures. That's what sets us apart, right? It's teamwork that's gonna make this work. So I feel like it's absolutely possible. We don't know when the train's gonna take off, as you mentioned, but hopefully soon. And it's definitely something that I would want to be interested in. And of course, I feel like what's also really interesting here is that sort of merger of computer science and physics, as you mentioned, because I found that so much of innovation that happens today, and this is also a theme that we touched upon with Sriram and Nuclear Fermium Research, who were on the show a little while ago as well. And I found that sort of like a common theme among a lot of different technologies is that innovation definitely happens within different technologies and within different fields, but a lot of major innovation happens at the intersection of different fields, right? When you start to combine AI and IoT, when you start to combine cloud and blockchain, when you start to combine these different technologies, that's when you get real innovation. And I feel like even just the fact that we have that sort of merger of the world of physics and the world of computer science, that in and of itself, I feel like lends itself to a lot more innovation because there's so much more we can do at that intersection, right?
Yeah,
So
like the use case, right? So if you take computer science and physics, and then say like I don't know, um, the climate, like you add a use case to that, and that's the intersection where the
mm-hmm.
message is important.
Yes. Yes, I completely agree, right? It's all about not only those two technologies you mentioned, right? It's also about that place where you're trying to apply it, trying to apply two different, fields to that one use case. I feel like that just really adds up well. As a matter of fact, related question from the live stream from Mag Deep actually. He's asking, is working on quantum computing only possible for postdoctoral people?
Yeah, that's a wonderful question. The short answer is no. The long answer is back to what I was saying about there's a quantum scientist. So you can really get involved with quantum computing with, I think it depends on how you want to get involved. So in general, if you have some linear algebra and basics of Python coding, you can get involved. And you can write code and you can write circuits and you can build applications. But if you are trying to create algorithms and you're trying to apply to research and you're really like redoing this space, that's when having a PhD will help. But a lot of the people I work with don't have that. I don't have a PhD in physics, and I think for you to get involved, it's really like what is your unique value add to the space? Is it the social media management that I was describing? Because people are going to need to talk about quantum computing. So you need the technical communication. You need, we have a video team that's creating a lot of videos online that helps people learn. We have educators to do, we have designers. So it's really whatever your skill is and applying it to the field of quantum. So you don't need a background in physics or PhD or that level to get involved.
Mm-hmm.
But I think you have to ask yourself, how do you want to get involved? And if it's really creating the research and creating the algorithms and advancing the use cases, maybe in that case, you might need it. But a lot of people are learning together, and the quantum computing is very, very, very open. So if you just want to get started and work on the side, I think you could do it. You wouldn't need the PhD.
Absolutely. I mean, I feel like maybe the a great sort of firsthand example that I've seen, there as I've sort of worked alongside a couple teams and a couple different orgs, for example, at IBM, there are lots of different teams that work alongside very technical teams that aren't necessarily technical themselves, right? So like, one of my friends, and I can link actually to a blog post where she describes this in detail, and her name is Michelle, and she doesn't work in a technical field, right? She does content writing for teams like the DB2 teams, and while she isn't technical, she's working with those technical teams to do things like documentation writing and creating videos for people to actually take a look at how developers need to go about using these tools. And within the field of technology, it's not just tech, which is something that I think is really important to understand. So if you're passionate about quantum computing, there's all sorts of areas around it that you can definitely work towards contributing to that field. It sort of also goes back to the episode that I had with Adam Holland a little while ago. He's an expert in cybersecurity, now is a senior director at GSK, previously senior director at Walmart. And he mentioned that depending on your mindset, you may or may not be the right person for a job in cybersecurity, actual operations. Maybe he would want to place you in a different field but still related to cybersecurity. Maybe things like regulatory management or risk assessment, these sorts of things. So I would say absolutely, I completely agree with you there, Anamita. It's something that really depends. It depends on what it is that you're interested in, what it is that you're passionate about.
All jobs are important. Like Tammy, you just said, like teamwork, right?
Yes.
Teamwork and great work. So what you're adding to the world is very important. What you're adding to the world, quantum computing is important.
Absolutely. Every contribution really does matter here. And so this actually brings me to another question. Now we're getting slightly more into the actual sort of quantum computing area of things. People, of course, are interested to hear more about how exactly quantum computing works. Now, in this episode, we're not going to go into the raw technical detail, but if you would like to sort of give us a little bit of an idea as to what are these, quantum mechanical effects, what is it about that world that enables us to have these brand new use cases? Really quickly, these questions are from Priyanka and Shiva on the live stream. They ask slightly more specific questions, like how are quantum computing and mechanics related, and what is entanglement, but maybe if we could just generalize to, how exactly does that world of quantum physics actually help us in the real world?
Yeah, so if we go back to what I just shared, quantum computing is a fundamentally different way of computing compared to a classical computer. So when you think of a classical computer, it runs on something called bits, so zeros and ones. A quantum computer runs on something called qubits, so very different from a classical computer. A qubit is a 0 and 1, and it takes advantage of different quantum mechanical properties, one of which is superposition. So it's 0 and 1 and everything in between. So the analogy that a lot of people use when they're describing what superposition is a coin flip. So if you're flipping a coin, a bit is like heads or tails. A qubit in superposition isn't spinning. So it hasn't actually hit and gone down to be a head or a tail, but it's that state flux when it's in spin. So that's quantum mechanical property number 1. When we think of quantum computing and qubits, there's 3 properties that we think of that make it fundamentally unique to classical computing. The superposition. The second one's entanglement. So entanglement is kind of hard to conceptualize, but it offers us this like very fascinating property that allows the magic of quantum computing to happen. So when 2 objects are entangled with each other, they're inextricably linked. So if we go back to the coin example, if one coin is going to be heads, the other one will also be heads. If one coin is going to be tails, the other one is also tails. There will never be an instance if 2 qubits are entangled that one will be tails and one will be heads. So when we think about quantum computing, you have 2 qubits that will get entangled with each other. So whatever one will read, the other will also do the same thing. So in quantum mechanics, when things are entangled, it could be anywhere in the world. So I could be in New York City, and if I'm entangled in Toronto, if I'm wearing a pink shirt, he's wearing a pink shirt. If he's wearing a white shirt, I'm wearing a white shirt. So that would be an example of us being entangled. So the third property is interference. And this really has to do with waves. So if you go back to your thinking about like the ocean. You have a wave going in, and then another wave comes in. You can see the wave going up based on constructive interference or destructive interference. And that the reason why waves are such a big deal and interference is such a big deal is that's how we communicate from a classical computer to a quantum qubit. So for the qubit to actually have a response, it happens in pulses, and those pulses are these waves, and these waves attach to each other. So the wave will actually give communication to the qubit, and the qubit, if it's entangled with something else, will give some sort of read and then give out a pulse, and then that wave will then come back, and you can interact with it on your classical device of if it's a 0 and 1.
So, what fascinates me about the world of quantum computing is that it's so fundamentally different from classical computing, as you mentioned, right? Being able to, at the end of a quantum circuit, actually, collapse that final superposition and measure the state of all your qubits and actually interpret that from a classical computer, I feel like that is perplexing in the sense of, as a regular developer, it's almost confusing as to what mindset should I have as I go into quantum computing, right? And the way that I've previously described this is that as a developer, you almost, and take this with a bit of a grain of salt, but you almost have to, forget what you've learned about classical computing, because quantum computing is really completely different. The word computing is still in the title, but it's not the same. So, and so you really got to relearn a lot of these different, very fundamental concepts and start to code at a very low level, in order to really, be able to interface, I would say productively, with quantum computers. And so, could you maybe give me an idea as to how, or what would you say the mindset of a developer should be? Let's just say, I'm a developer and I work a lot with classical computing, of course. What should my mindset be as I want to go and learn quantum computing? What would I need to learn? What would I need to do in order to actually start using quantum?
Yeah, so I think the first thing to think about is what you want to put in. So there's different devices. IBM has a device. We have our open source development framework called Qiskit. That's the language you use to code on an IBM software or IBM hardware. So if you know Python, you can work with it. If you don't know Python, different companies have different programming languages for quantum. So there's Q Sharp and then C Sharp. There's just different options for you to explore. So I would say reflect on what you do know and then see if there's a parallel open source framework, coding language that you can use to create it. You don't need to necessarily learn a new one, but there will be some benefits to learning Qiskit that applies on quantum hardware for IBM versus another because of what's open and accessible to you.
Mm-hmm.
The other thing that I would say is almost every single software development framework for quantum is open source. So go join those communities. Go join those communities and see what's happening and see what other people are doing and learn, because that's what a lot of people are doing. The quantum computing community right now is very, very small. So, and it's very global. So you'll be able to be interlinked with people around the world who are also trying to do the same thing as you. The third thing is, as Tanmay just said, that you have to go down to these like very, very basic levels. So you have to learn a little bit. So there's, when you're thinking of just like circuits and gates that you're creating, there are different gates in a quantum computer, and some gates function a little bit differently. So you will have to spend some time just understanding the basics of it. There's a lot of education for you online where you can do that. There's textbooks that people have written online and also physically that you can explore. There's videos, there's written text. So it's really like, how do you like to learn? Find it and play with it. And just like anything else, it's really, you have to try it. And as you try it and you code with it and play with it, you can, you'll get involved and be happy with what you're creating. A lot of applications right now in quantum are fun. So a lot of people have created games. So you can look at different games that people have created with quantum, and you can use that as kind of a way for you to get started, or you just maybe the circuit to see what happens. But there's many, many ways to get involved. But the biggest thing is ask yourself how you want to, what you want to contribute, how involved you want to be, and then really be honest with what you know, and that's going to make your barrier to entry lower.
Very nice. I gotta say, I do really enjoy the little Qiskit like notebooks that IBM's actually put together on the Q experience. Those are things that helped me a lot as I was initially getting into the world of quantum. So definitely do check those out. I will put a link to those in the description as well. Now, it's funny that you mentioned games because I have a bit more of a general question, but we did get a more fun question from Power Ups on YouTube. They're asking, can quantum computing be used in gaming?
Yeah. Well, I think you'll see a lot in gaming websites. I don't know what kind of a gamer you are. I'm not a gamer myself, but they talk about quantum computing because advances in quantum computing could potentially change how gaming is done. But what quantum computing is really good at is giving you more options. So instead of the 0 and 1, you get powers and options and exponentials. So like 2 to the 3, 8 possibilities versus 3 possibilities. So because of that, gaming can be a little more fun, and it can be more unpredictable and more generative. And people have created a lot of different examples of sample games built on a quantum computer, and it's a great way to get started. We have a YouTube video on our Qiskit YouTube channel about quantum Pong. We have 2 researchers on the IBM quantum team that have created a lot of different games, including Minecraft with quantum computing, Flappy Bird on a quantum computer. I worked on a game that was like a figure 8 ball. So when you would type something in, and it would say like, yes, definitely do it. It was built on a quantum computer. For Halloween, someone created a Harry Potter sorting hat. So there's a lot of games that you can create, and those are actually really easy ways to get started. Tammy, I'm happy to send some like GitHub links if
I would
you
love
think.
that. That would be helpful. So I'll go ahead and put those in the description as well, so you can take a look at that. But yeah, quantum computing for gaming is interesting. If I remember correctly, this was a while ago, so I may not remember it completely right. But there was an example of using the IBM Q toolkit for like terrain generation or something of that sort. Yeah, and I feel like that was one of my favorite examples.
That's the same researcher on our team that created the Minecraft.
Ah,
Um,
that that makes sense.
what we do is we have a lot of hackathons around the world that all of you can participate in. And that terrain generation actually started from one of those hackathons. And then it evolved into something really cool, honestly.
I can imagine. I mean, I gotta say, even like with regular, classical computing, terrain generation is just one of those things that always makes me think that's a really interesting algorithm. Regardless of the actual compute that goes behind it, just seeing the, emergent output from these sorts of systems is generally fascinating to see. And I mean, I can imagine with quantum computing, it must be even more fascinating. So I'll put those links in the description for sure. All right, so now I want to take a little bit of a shift, and I want to answer a question from Work in Progress really quickly. And this is from the live stream. It's a bit more technical, but this is something that I do have a little bit of experience with. But we're also going to have another guest on the show soon with much more experience than I on this topic. And he's asking. And specifically, his comment is, "I'm not an expert, but I would guess, how can you actually use qubits and quantum computers to write efficient algorithms? How would the compilers work to do that?" And so, what I would say is that, first of all, if we look at the world of classical computing, first of all, processors themselves have gotten incrementally more and more advanced over the years. And today, even if you're writing, down in assembly, you still don't have total control of the computers that you're writing the code for. Because at the end of the day, your instructions are still very, very much pipelined, and they're very much parallelized in terms of their, execution patterns by the CPU. Things like branch prediction are still going to be happening regardless of whether you want them to or not. And so, even generally with regular computers, down at the hardware level, we don't have that much control over them as we used to. C, for example, used to be a really low-level language. Nowadays, it's actually a pretty high-level language. And thanks to compilers like Clang and LLVM, and thanks to contributions made by companies like IBM to these open-source projects, we still have that illusion of it being a low-level language because the compilers can help us optimize our code really, really well. However, I would say that we've already got a lot of great technology similar to this for the world of quantum, and of course there's a lot more to come. But like, for example, today, what I find really interesting is if you go over to the IBM Q experience and you were to create, For example, that same delayed choice quantum eraser circuit I was talking about that I've built, you have all these different interactions between different qubits that you just put there arbitrarily, but there's only a certain number of ways those qubits can be connected down at the hardware level. So there are actual, compilers going down into your code and trying to figure out how they can map your circuit to the actual topology of the quantum machines you're trying to run them on. And then it's trying to say, all right, how can we optimize this? Do we see little, sections of code that we know we can optimize, just like how LLVM would say, hey, if you're running these instructions, we know we can bring it down to these. So I would say that there's a lot of work to be done at that hardware level, or sorry, not even the hardware level, but that intersection of hardware and software that will then translate to a better developer experience. Still a lot of work to be done, but there already has also been a lot of work done that I think IBM is really at the forefront of doing. So that's personally something that I'm really interested in. But anything to add to that, Anamita?
No, I think it's one of the spaces that you watch. So compilers is something that we're working on, and I think a lot of people are working on. So how do we see what what changes are going to happen?
Yeah, it's pretty fun, and I gotta say, just like sort of going back to your point, Anamita, just like how as developers we kind of have to almost in a way unlearn a lot of the things about regular classical computers, just because down at the fundamental level logical gates are different on quantum computers, right? I feel like with the logical gates that we have access to with classical computers, they translate to certain naturally sort of evolved high-level constructs, things like if statements and loops and functions and things that just kind of make sense to have on a classical computer that we take for granted, which then when you translate over to quantum computing, because those gates are different, the sort of high-level constructs that they map to are also going to be completely different. So I feel like that's definitely going to be a little bit of a learning curve for most developers, but it's going to be interesting to see.
Some overlap. So like the XOR gate on a classical computer.
Yeah.
Do you say XOR or do you say XOR? I find people say it differently. But so
Excellent.
classical computers will have the same thing on the quantum computer. But then there'll be new gates that you've never even used. So like the hammer gate on a quantum computer is different, and you don't have that on a classical computer. So it's learning, unlearning, adding on to what you already know, and then like brand new things.
hmm I agree. There's going to be some parallels to draw, but there's still going to be a lot of new stuff to learn as well. All right, so now there's a question from Vishnu, and this one's a little bit more out there, but I do want to ask, and he's asking, I'm doing my master's in AI. Can you tell me how I can link AI and quantum computing, and how I can use them to make an outcome?
Yeah. So AI, people are using quantum computing to find better patterns, optimize. The algorithms where quantum computing will work very well with when it comes to AI are the exponentials. So I would say, like, look at the algorithms that do have exponents to them. Those are the ones that will probably have a better translation in quantum computing. There's also in Qiskit, which is the open source development framework that we use for IBM Quantum. There's a module, if you go to the Qiskit GitHub, on AI, and you can go in there and look through and see what other people have done. There are also a lot of open tickets and issues where people are interested in working. Went up and start like working with the community there. And then there's a lot of research that's coming out a lot. So I would look at what's in archive and see if there's an application that you can put in. We just there's a paper from someone on our team that looked at quantum variational classifiers. So how do we take classical like classifiers and then apply it to quantum and work with these different dimensionalities and spaces. So I would say, like basic level, look at your algorithm, go look at Qiskit and see what's already out there, and then read papers on it and see if that's possible.
Very nice. I gotta say, it's interesting to see what kind of progress we've already made. We can implement simple classical classifiers on quantum, which I think is really interesting. If I remember correctly, again, this has been some time since I've seen this notebook, but there was also a notebook on SVM kernel tricks implemented with quantum. So that's also definitely really interesting. So I'll link to that as well. So you can. It's a lot of stuff to link to, yeah, but it's one of the most fun examples I've seen. All right, so now there's a question from Rajat on the live stream. They're asking, can quantum computing be used to help in research for fields like cancer treatment, which I'll just generalize to healthcare. So have we already seen any use cases that you're allowed to share on like quantum computing in healthcare?
Yeah, I get this question a lot, and I think right now is quantum computing isn't really at a point where it can do that, but there's probably for it too in the future. So with the current hardware and the current abilities that we have, it's not enough to actually make advancements in that field for now.
Understandable. Yeah, no, that makes sense, right? We're starting to see those sorts of base use cases or problems that we're starting to solve that would eventually be used as building blocks to solve larger problems in healthcare, I think. But we're not completely there yet with actually applying it.
And I'll use this to plug something very interesting that I think about all the time, which is ethics. So when it's a new field, right, like you have to think about what's the right ethical way to do it. What are the societal implications that we'll have? And I alluded to this previously about how we talk about tech will influence how we use it. So it could be from like policies that we get, like the city of San Francisco banned all um, visual recognition and all like computer vision, right? But the city of New York has been using it for so long, so it creates these different realities that we live in. The same is true for quantum computing. So how we talk about it now will influence these laws and other things that will happen. So when we think about applications like cancer research, like pharmaceuticals, like which governments will have access, these are questions that we need to start thinking about right now. These are applications that we need to start thinking about right now because how we create the technology right now needs to take into account of what it will be used for in the future and the policies and frameworks that we create. Because if one pharmaceutical company has access to quantum computers and the others don't, based on how we've built the structure, then it could have this monopoly for this one drug, which then drives prices up, and then that drug could maybe be in one specific country and other people will get it, and then it has like real life or death like type applications. So when you do ask questions like cancer or how it could be used for simulating the brain, maybe like what are the right ways to be using these new technologies? And those are the questions that you should be asking yourself. Like who's going to use it? How are we going to control it? Who should be in the room when we think about these sort of problems? Because when you go into issues like this, it opens this huge can of worms of how will this technology be used and by whom? And who
Yeah.
will it benefit everyone? Will it benefit certain people? There's so many questions.
Yeah, I gotta say it's almost hard. I would say it's almost equally as hard, apart from just researching and developing the technology, to make sure that technology ends up in the right hands and used for the right things. And that's always been a challenge that we face as humans, all the way from something as simple as the invention of fire to something as complex as quantum computing, right? I feel like that's a challenge that we've always faced, and it's going to get progressively more complex to figure out these issues because there's all sorts of unintended consequences to things that we do. We can't even just say, it's very easy to say that everyone should have equal access to something like quantum computing, but it's very difficult in practice to actually implement that. And we've started to see some initiatives working towards that. Again, I feel like things like IBM Q Experience are that sort of great equalizer, enabling everybody to sort of get access. But still, it's sort of once we have larger computers, when we have greater capability to do more advanced things, like for example, actually simulating, for example, a brain and being able to simulate drugs and how they interact with molecules in our body, it becomes progressively more complex to sort of draw that line and figure out how exactly people would or would not get access to the technology. So it's definitely an interesting field, but it's something that we've got to think about. So I appreciate you bringing up that subject. And now, actually, another question from Power Ups again on YouTube, but this is something that I wanted to ask you as well, and that is that quantum computing, or at least the way that I see it today, this could be because it's very experimental, but it's the kind of thing that's really really going to help out, as we mentioned, with certain tasks. We've already mentioned that it's not going to replace classical computers. You're not going to be liking someone's post on Facebook with a quantum computer, but the thing that I was wondering is is quantum computing the kind of technology that's going to be more of a, I guess, B2B thing, where it's businesses that are using it and that sort of advantage that new user experience trickles down to the user, or is it something that users are directly going to interact with through classical computing, right? Maybe a good analogy would be things like, the NVIDIA DGX A100, the IBM Power 10 machines. Right? Consumers aren't going to buy a Power 10 machine, plop it in their basement, start using it, but they would interact with it through an airline, right? So their airline would be using a power or a power machine or a mainframe, so they're indirectly interacting with it. So what do you think? Will quantum computers have noticeable impact on the consumer level, or will it trickle down through business?
Yeah, it's a great question. So I think the real answer is I don't know. I can't really predict where it's going to go. But if I speculate, I think it's going to be a combination of both. I think there will be implications for consumers because businesses are using them, and we will have that change. I think businesses will use them, and that will also impact our lives. So if we think about like just even how AI is being used under the surface, right? Quantum computing will be used under the surface. We don't really know how the technology is. We just care about getting our current problem at hand solved, whether it's like getting on the right plane in the right seat. Quantum computers can be used in the background. I do think that this is a field similar to AI and other technology that's going to be constant research in it. So we will probably be partnering with businesses and with students and professors and institutions to co-create and do research with them. So in those cases, I think will definitely be a B2B interaction of how are we creating these technologies and algorithms for your specific business use case, and how are we creating these algorithms on a very fundamental level with institutions, and then from there it's constantly optimizing what's already being used under the hood. So I think it'll be a combination of both, but how it's realized is going to be unique to the user and it's going to be unique to the business.
Mm-hmm. It's I will say you're right, right? Like when we have technologies that help out businesses, eventually those advantages do trickle down to consumers, right? Like Google has their TPUs, right? Eventually, when you use Google Assistant, you're going to interact with them in some way, and that's going to enable a new experience, even if you don't realize you're using a TPU, right? Even if you don't realize when you call your bank, the chatbot's powered by Watson Assistant, still are using Watson Assistant. So that's going to be interesting to see sort of where that impact lies for consumers and just how obvious it is that quantum is impacting. Will it be more like AI, where you kind of use it but you never realize it, like fall detection on the Apple Watch, you never realize that's machine learning, but it is, or will it be more direct? This is brand new. I couldn't have done this without quantum, sort of thing. So I'd be interested to see what exactly that looks like. All right. So now there are actually two questions from Akash. One of them I would want to take up really quickly, but of course, Anamita, I'd love to hear your thoughts on this as well. And Akash is asking, is there any relationship between, in classical computing, what we know as parallelism and concurrency, and then quantum computing in general? And I will say that due to some of the analogies that I've seen some people use with quantum, I feel like this sort of almost this misconception that what we think of as parallelism in classical computing translates very directly to quantum computing. But I don't necessarily think that's the case, right? I don't think, as a matter of fact, quantum computing isn't just doing lots of things at once, like a classical computer. It's quite literally redefining the fundamental fabric on which we compute, the gates that we can use, and the laws of physics that we can leverage in order to make it so it looks to us, if we abstract away the computing, that things might be happening at once, right? So, like, for example, as you mentioned, where you can take an exponential algorithm and sort of reduce the complexity, the time complexity. If you were to abstract away the compute altogether, sure, it might seem like multiple things are happening at once, which is why it's faster. But that's not actually why it's faster down at that compute level. It's not because we're doing multiple things at once. It's because we've redefined the fabric on which we're allowed to run the compute, and suddenly we have this gate which makes it look like we can do multiple things at once. But anything to add to that, Anamita?
No, I think it goes back to the three principles, right? And superposition, entanglement, those three principles that effectively enable exactly what you described.
Absolutely. As a matter of fact, there's actually a great extension to the question asking, is there any programming language specific to quantum computing from Akash? I mean, as we've mentioned, there's Qiskit for Python, and there's Chasm, or how do you pronounce that? Q assembly, what?
Yeah, I actually don't say it out loud very often, but I say um, Sharp. There's like there's so many. Like every single hardware company has their own. But I'm obviously going to be a strong proponent of Qiskit, which you can go to at qiskit.org, qiskit.org. And then from there you can access our GitHub. Qiskit.org also has a lot of our learning material, events. We host live streams. There's a lot of ways for you to get involved, and going to that website will be your first stop. on the train.
Absolutely. It's the first stop on the train, and I feel like it's going to be the first sort of interaction with quantum for a lot of the people joining the live stream today. So make sure you do check that out. Links will be in the description. Now another nearly final question from Shivam. He's asking, I study at IIT Delhi. I've done a course in quantum computing. I have done an internship at IBM for quantum gate minimization. Great job. Are there enough industrial research labs in quantum?
Ooh, are there enough? I kind of want to say no because there's probably never going to be enough. Um, and I think there are more and more research labs. So what you find is there's two types. There's research labs that have been researching for decades. They've been around. And India is actually one of those very interesting markets where the professors in India that have been in the quantum computing space have been in it for a very long time and are very, very mature. Then when you go to other parts of the world, they're just spinning it up. And it's true for a lot of the places in the United States where maybe these certain professors have been working on it for a while, but now they want to add courses in quantum computing. So they're spinning up these new departments and related to that labs. So I think the answer is like, no, there's probably not enough. And I would say the same is true for India too, where I think new labs will start spinning up, especially attached to different universities. And then there's going to be industry partners that will happen. Like I know IIT Roorkee just might a partner with Microsoft. There's also an IIT Hyderabad partnership that's happening. So I think looking at the industry partnerships will be another big a big impact of where these labs will start.
Mm-hmm. So I love how you mentioned there's never enough quantum labs. Right. I mean, when it comes to really anything, there's never going to be enough. It's not like we can say, all right, we've got enough data centers now. Spin it down, no more data centers, right? But I do understand the context of your question, Shivam. Thank you for asking, and you're asking is there enough for me to be interested in actually doing this? But again, thank you, Anamita, for your thoughts on that. Now there's another question. I'm not sure if this is something that you would have thoughts on right now, but it is a question from the live stream. Aratrika asks, how will quantum computing impact our existing cryptographic systems?
Hmm. Well, if we go back to thinking about um, the exponential concept, right? Quantum computing is very good at taking a lot of things, processing it, and then giving a very simple output. So when you think about cryptography, that's one of the very easy applications of this. A lot of data, a lot of things, simple output. And there's a lot of people that are looking into what quantum can do for cryptography. It's like an entire field of research. Um, and I think my opinion is we're pretty far away from it having real change. And I think a lot of people are worried about, oh, I have to change everything now. But there's always advances in it. So it's not going to be something that's going to be so insane that you'll have to like reconfigure everything. And maybe it will be, I don't know. But I think we're far away from it actually being realized. And cryptography is definitely one of those spaces where it's uniquely positioned to be successful in quantum computing.
I completely agree. Like lots of the algorithms that we depend on fundamentally are algorithms that we can accelerate with quantum. So it's like kind of like how GPUs were like meant for games, but then we turned out to say, hey, we could use that for AI, and that led this whole new acceleration. It's like quantum computing wasn't built for cryptography, but turns out it's a perfect match. So I can't wait to see what we do with that. All right, those were a lot of questions from the live stream. Unfortunately, there were some that we couldn't even cover just yet. But again, if there are any more questions that we didn't get to, please feel free to put them in the comments, and we will make sure to answer as many as possible. Now, Ayush, I do see a comment that's saying, do we read the live stream comments? Yes, we do, and we're answering any questions you have. Unfortunately, we're nearing the end of today's live stream, so we won't be able to answer more. But again, feel free to put them in the comments when the replay of this video is up, and we'll go ahead and answer them there. Now, Anamita, before you go today, there is one more thing I wanted to ask of you. As you know, we've got all kinds of people, joining TechLifeSkills today. And if you had one, sort of closing message that you wanted to share with them, what would that be?
Well, for those of you who don't know, today is National STEM Day in the US. And it's a very special day for me because I do a lot of work with the American Association for the Advancement of Science to increase our representation in science. So how do we get more women and girls involved? How do we get people from different backgrounds involved in STEM? So my message for you all is, if quantum computing isn't something you've considered, maybe take a moment to consider it. And if it's not quantum computing and it's another part of technology, then fantastic. Stick through it and bring people with you as you go through, because representation really matters. And if you need the help, I think ask for it, because you're uniquely positioned to do uh, change in the world. So I would encourage all of you to keep doing what you're doing, like watching these shows and contributing to science and doing it openly and visibly for each other.
Thank you, Anamita. I really appreciate it. It's great to hear that it's National STEM Day, and hopefully, this inspires a lot of people, even joining today to get deeper into the world of technology. Again, you should be doing what it is that you're passionate about, but I believe that technology is one of the things that we don't necessarily introduce to students enough, and there's so much of a stigma around it, especially things like quantum computing. So, again, my goal through shows like this, and thank you, Anamita, for coming on, my goal by having you on and by hosting this show today is precisely to make those concepts more accessible, and to make it so everybody can figure out what it is that they're passionate about, especially if it has to do with technology. So I really do appreciate you coming on the show today, and I also appreciate everybody joining the live stream. So thank you very much to everybody. I really do appreciate it. Once again, TechLifeSkills is held every week on Sundays in the morning Eastern time. So make sure you join us next week. We're going to be covering machine learning technology in a bit of a deeper way than we usually do. And so we're going to be talking about a really interesting company. Can't say just yet, but join us next week. It's going to be a really fun episode. And so, I've learned so much about the world of quantum computing today. It's an area that I've always been very interested in, and I can't wait to work more on in the future. There's videos coming soon on the YouTube channel. And of course, any other questions, I will go ahead and reply to them in the comments below. Especially Joe Zwinger, I see Nitin, a couple questions. We'll go ahead and answer those as well. But thank you very much, everyone, for joining in today. Thank you, Anamita. Really appreciate it. And goodbye, everybody.
Thanks for having me.